So in this video, we're going to talk about quantities, specifically representation of these quantities. In physical quantities, we have two different methods of representation. The first one is the scalar representation and the other is the vector. A scalar is basically a number. It's kind of the definition of a quantity. Let's say that if your car is going with a speed of 20 miles per hour, then that's the scalar, the measurable quantity of that system. We also call that speed. But a vector is the numerical value plus the direction of that quantity. A good example would be the velocity of a system. If you say that you're going 20 miles per hour to the east or some other direction, you just define a vector. So that's what a vector is. And to represent them, we have several methods. But before we get into that, let's talk about a little bit of trigonometry first, because we're going to use it quite a lot in physical calculations. So this is our basic triangle. It's a basic 90-degree triangle we got here, and let's call this angle theta. So we have the lengths A, B, and C. I'm pretty sure that all of you are familiar with the Pythagoras theorem. A squared plus B squared equals C squared. That's the most basic formula for trigonometry. But for our sake, first we're going to talk about a unit circle, and we're going to understand how this circle and this triangle is correlated with each other. So the unit circle is basically a circle in a coordinate system with a radius that is equal to 1. It's just a basic circle. What we use the unit circle for is to define vectors in a way. So we can take any point on the circle. Let's connect that to the origin of our coordinate system. And since this is a unit circle, every radius, each length of that would be equal to 1. So we want to know, for our purposes, these side lengths. How do we know that? Well, if we know the angle of this length with the horizontal axis or the vertical axis, it doesn't really matter, we can get a shape which is similar to a triangle. Actually, not even similar, it's just basically a triangle. And what we can get from this to achieve these lengths is actually quite basic. So we have different functions: sine, cosine, and tangent. So on a triangular basis, the sine function is defined as, well, the sine of theta function is defined as the opposite length to that angle divided by the length of the hypotenuse, which is this length over here. And this is called the adjacent. So our sine theta is defined as A over C. Similar to that, our cosine theta is defined as adjacent over hypotenuse, which is B over C. And our tangent theta is opposite over adjacent, which is A over B. An easy way to remember these would be through a method called the SOHCAHTOA. The sine is called the SO, the cosine is called CA, and the tangent is called the TOA. These are just abbreviations to our formula. The sine theta is equal to the opposite over hypotenuse. The cosine theta is equal to the adjacent over hypotenuse, and the tangent theta is equal to the opposite over adjacent. So this is all cool and neat, but it still doesn't really explain why exactly, like how can we find these lengths through these formulas right here. Well, I mean, if you have one value and the other, you can find the rest. We know that our hypotenuse in this case is always 1. No matter where you take that point, it's still going to be 1. It doesn't really look like a 1 because I drew this shape quite bad, but trust me, it's a 1. And what this allows us to do is that we can define this length as cosine theta, and this length as sine theta. But why is that? Well, the why of the question is because that this length is always 1, and our cosine theta is defined as adjacent over hypotenuse. And since in this case our hypotenuse is 1, the cosine theta basically gives us the adjacent length. And it's the same for the sine theta. Since it's defined as opposite over hypotenuse, and our hypotenuse is 1, we're just getting the length of the opposite. Of course, this wouldn't always be the case. Our length, our radius wouldn't always be 1 if we were dealing with other circles. Let's say that you have a circle with a radius length of 2. Well, to find this length, what you're doing is multiplying the radius by the cosine theta. And for this length is multiplying the radius by sine theta. Because it's still going to give us the same answer. Cosine theta is adjacent over hypotenuse. Our hypotenuse is the r. These will cancel out and it will leave us with adjacent. And it's the same case for the sine. So how is this helpful to us? Well, it's quite helpful when you're dealing with polar coordinate systems. We have two coordinate systems. One is called the Cartesian and the other is called the polar. The Cartesian is quite helpful. We have, I drew that quite bad. We have two different axes, or three, depending on what kind of dimensions you're working on. You can take any point you want, and when you gather that with the origin, now that graphically you define the vector. You can say that this is vector A. And to define this in a Cartesian coordinate system, you just basically take the values of the horizontal axis and the vertical axis. So let's say that this is 3 units long and this is 5 units long. We can represent the vector A as 3i plus 5j. So this addition right over here is not really an addition. You can think of this like that. If you're taking this as the quantity of the vector, I actually drew that wrong. If you were representing the quantity of the vector, you'd have these things over there. You can represent it like this. And when you want the quantity of that, you can apply the formula of our famous mathematician, Pythagoras. That would give us the result. But for a polar coordinate system, things are a little bit different, because for a polar coordinate system, you can imagine it as we have unit circles of any length we want, of any radius. The radius of the unit circle would give us the length of our vector. And the point we take that on that circle can be represented with the angle theta. This is how a polar coordinate system works. And we use that trick of trigonometry that we learned just then to convert polar coordinates into Cartesian, or the reverse, whatever you fancy. So now we know how to represent these vectors, but can we do operations on them? Like addition, subtraction, multiplication, division, like the basic operations. I know that we can do that with scalar values. I've been doing that since like primary school. For vectors, it's a little bit different, but it's not really hard. Let's say that you have a vector A and a vector B. These are not good representations, but just stay with me. Let's say that this is 3i plus 5j, and this is 4i plus 2j. It definitely isn't, but it really doesn't matter. So to add these guys together, we have a couple of methods. If you want to address it graphically, what you're going to do is that you're going to take the end of the arrow or the beginning of that arrow for one vector, and you're going to add that to the other end of the other vector. So I took my vector A, I placed its arrow on here, and I'm placing vector B right here. Why am I doing that? Well, because when we're adding these two vectors together, we're actually adding triangles together. Because we just saw that we can represent any vector just like a triangle, with its values on the horizontal axis and vertical axis. What we're doing is just we're adding up the vertical components and the horizontal components together. And when we place these two vectors from tip to toe, we can end up with the hypotenuse of our bigger triangle. And that will give us the resulting vector, A plus B. For our case, we can say that it's 7i plus 7j. And for subtraction, it's basically the same, but since subtraction can be thought of addition, but with a different sign of one of the quantities. So when you see A minus B, you can think A plus minus B. So that means we're going to take our A, but we're going to reverse our B. We're going to do the same trick, and now we have A minus B. And as in the numerical aspect, it works the same. That's 3 minus 4, which is minus I. That's 5 minus 2, which is minus 3j. For multiplication, we're going to see different methods later on, but let's first understand how we can multiply a scalar quantity and a vector quantity together. It's pretty straightforward. If you have a vector A, when you multiply that with a scalar quantity, let's say m, you're just multiplying each of the values of the horizontal and vertical components together. So the resulting vector would be the addition of these multiplied horizontal and vertical components together. If you multiply the vector A by 2, you're going to get 6i plus 10j. It's pretty straightforward. So when we want to multiply two vectors, not a scalar and a vector, two vectors, we're going to do something a little more different. So we have two types of this. One is the scalar product, or sometimes known as the dot product. The other is the cross product, or sometimes known as the vector product. This is just denoted by a dot in the middle, and this is denoted by a cross symbol in the middle. So, with the scalar product, what we do is pretty straightforward. If you have values such as 3i plus 5j and 2i plus 2j, you're adding the horizontal values, I'm sorry, not adding, multiplying the horizontal values and vertical values together. The resulting vector is the addition of those horizontal and vertical values. So this is 6i plus 10j. That's our scalar product. This is the operation on a Cartesian sense. If we do it on a polar sense, meaning that we have lengths RA and RB and angles theta A and theta B, what we're going to do to find the scalar product is just multiplying those lengths together and just taking the cosine of the angle between. You can imagine it like this. This is A, this is B. When we're taking the scalar product of this, we're basically taking the projection of one of these vectors onto the other. By doing that, we're getting both of these vectors parallel to each other, so when we multiply them, it actually makes sense, right? Because when you just multiply the values of the lengths of these vectors together, that doesn't really make any sense. They're looking at different directions. That multiplication doesn't really add up. But what adds up is if they were looking at the same direction parallel to each other, then we could multiply these together just like a scalar quantity. And that's what we're doing in here. For the cross product, it's a little bit different. I'm not going to show you the Cartesian sense of it because, well, that's literally, that's literally linear algebra. And we don't really need it for the moment. I'm just going to show you the sense of the polar coordinate system. For the cross product, you need, if you're working with a two-dimensional system, you need 3 dimensions. Because the resulting vector is going to be in that third dimension. What I mean by that is, let's say that this is our vector A, this is our vector B, this is going to be our cross product. And how do we calculate that is rather simple. Just like we did in the scalar product, we multiply the values together, but instead of taking the cosine of it, we're taking the sine of it, the sine of the angle between. And the resulting direction of the vector can be calculated by something we call the right-hand rule, which is something that we're going to use quite a lot in the future. The right-hand rule is basically that you can take your hand, so this is your palm, these are your fingers, you can take your hand, let's put one of the vectors in this direction and one of the vectors in this direction. The resulting cross product of them would be in this direction. So you're basically representing a 3-dimensional polar coordinate system with your hand. This denotion, by the way, it means that the vector is going towards out of the screen. If it was presented like this, it would mean that it's going into the screen. You can think of it as like an arrow and a bow. the back of the arrow could kind of look like an X. The front could just look like a dot in here. That's the idea. So we're going to solve, cut this part out. 1, 2, 3. So we're going to solve a couple of problems on what we've just learned. Let's start with this one. The polar coordinates of a point are equal to r 5.5 meters and theta equals 240 degrees. What are the Cartesian coordinates of this point? You can stop the video and try to figure out by yourself. I'm just going to solve it in here. So let's draw our polar coordinate system to understand this. So this is our vector. Let's call it A. The r, the length is equal to 5.5 meters, and this angle is 240 degrees. So you can calculate it in a longer way, but another thing that you can do is that since all of these sections are 90 degrees, 180 degrees, this is at 270 degrees. Since this is 240, this angle right here leaves us with 30 degrees. This is much more manageable for us to calculate since we don't really care about the specific calculations. We just want the Cartesian coordinate of this point. So to calculate this, what we're going to do is we're going to multiply the length by first the cosine of that 30 degrees and by the sine of that 30 degrees. So let's use our handy calculator for that. 5.5 times the cosine of 30 degrees. Well, it's about like 4.76 meters. And the same thing for the vertical component, which is the sine of 30 degrees. And that's about 2.75 meters. So what you should be careful with is that since we didn't measure it with this angle but with this angle, now you need to be careful of the sign of these values. So since we're taking the horizontal value here and the vertical value here, so cosine 30, that actually gave us the vertical component of this vector, and as you can see, it's in the negative area, so it's going to actually be minus 4.76 meters. And the same thing is true for the vertical components. That's actually going to be minus 2.75 meters. So for a second question, let's look at it. A pedestrian moves 6 kilometers east and then 30 kilometers north. Find the magnitude and direction of the resultant displacement vector using the graphical method. So what we're going to do is that we can imagine these movements as two different vectors, and we just need to add these vectors together. That's quite easy. This is our displacement of 6 kilometers on the east, and this is our displacement of 13 kilometers on north. This is our resulting displacement, which is the vector that we would like to find. To find that, we can use Pythagoras' formula, and let's calculate that with our calculator here. That's about 14.3 kilometers. So we figured out the total displacement, the length of our resulting vector. But we also want a direction. We can't really say east or north in this case. We want to find the angle of the direction. How we can do that is actually something that I haven't showed you, but it's quite simple. So we know that tangent theta of any value is equal to the opposite and adjacent. So if we want to find the theta, we can basically take the inverse function of the tangent for the value of the opposite divided by the adjacent length. For our case, that's theta equals to tangent inverse, and the inner value is opposite, which is 13 kilometers, divided by adjacent, which is 16 kilometers. Let's look at that. With our calculator, that's about... It's actually really quite a small value. It's like... Actually, that's not right. It needs to be 1.14. Okay. So... our next question. Vector A has a magnitude of 8 units and makes an angle of 45 with the positive x-axis. So let's put our coordinate system right here. Our positive x-axis is this. It makes a 45 degrees angle. It has a unit equivalent to 8. This is 45 degrees. Vector B also has a magnitude of 8 units and is directed along the negative x-axis. Using graphical methods, find the vector sum A plus B and the vector difference A minus B. So the vector B is directed along the negative x-axis. So it's actually on top of our x-axis. This is B. That's going to be 8 units long. So A plus B, let's look at that. That's easy. To find that, we can put one of these onto the other. Let's put the B on top of A. This is A, this is B. We know that this angle right here is 45 degrees. And since these are parallel to each other, this angle right here is also 45 degrees. What we need to find is this. So there are two different things that we can do here. It's actually kind of a long calculation, so I'm not going to do it. But what we can do is that first is that we can use the cosine formula. If, for those who don't know, let's say that this resulting vector is C. The cosine formula is basically tells us that the length of C is equal to the length of A squared plus B squared minus 2 times the length of A, the length of B, and the cosine of the angle in between. If we do the proper calculation, we can find the length of this resulting vector, and we can most easily find the angle of this vector, since we can actually just find it by geometric approach. Since we know that these two are equal to each other and this is 45, we can find the angles in here, we know the angle in here, we can find this angle. Another thing that we can do is that we can take the horizontal and vertical values of this vector, horizontal and vertical values of this vector, which in our case, this vector doesn't really have a vertical value, it's just 0. We can add them together. and that would give us the result in a Cartesian coordinate system. And if we want, we can turn that back to the length of that vector and the angle of that vector. And for the vector difference, what we're going to do is that we can take the A as like this, and we're going to reverse the B to this direction and put that on top here. This is B. It's 8 units here, 8 units here. This will be our resulting difference. And we can calculate them with exactly the same way. Since that these are parallel, we can find the angle in here, and we can apply the cosine formula to find the length of this. Or we can find the horizontal and vertical components of it. Oh. Okay. So this is also a basic example. We need to find the addition of these vectors, which will give us the resulting vector C. This is most quite handy because we can just add the horizontal and vertical values. We can't really use the cosine formula. Well, we can technically, but that would be really hard. We would need to, first we would need to take these two vectors and find the addition of those, and then later on we could add those together with the same cosine formula, and then we can find the C. But we don't really want to work with that. Instead, we can just find the horizontal length of this, vertical length of this, horizontal length of this, vertical length of this, and these already have just one type of length. This is just on the horizontal axis, this is just on the vertical axis. We can add those up together, and we're going to find the value of these lengths. Later on, if we want to, we can convert that to the polar coordinates. So our last two questions. Vector A has a magnitude of 5 units and B has a magnitude of 9 units. The two vectors make an angle of 50 degrees with each other. Find A dot B. This is quite easy. I already taught you how to calculate this. First, obviously we want to find the magnitude first. A is 5 units, B is 9 units, and the angle between is 50 degrees. If we calculate that with our calculator, that would give us a result of about 29 units. This is our magnitude. So two vectors are given by A is equal to minus 3i plus 4j and B is equal to 2i plus 3j. Find A cross B and the angle between A and B. So how about we first represent these in our Cartesian system? So A is minus 3 plus 4b. That's something like about that. That's minus 3 units plus 4 units. And B is plus 2 plus 3, which is something like that. This is plus 2, this is plus 3. So we want to find the cross product of these two vectors. So I'm going to come back to the direction of it later, but first we want to find the value. Finding value is not hard. Let's first convert these into polar coordinates. We can do that by Pythagoras' theorem. This would have a length of 5. And this would have a length of about, let's look at that. of about 3.6. And to find the magnitude of the cross product of these, what we're going to do is we're going to multiply these two values together, and we need to multiply it by the angle in between, which we already need to find. So how do we find the angle in between? Well, like I showed you before, we can find the value of any angle of these vectors by the inverse function of tan with the input of opposite over adjacent. I'm going to calculate it for both of the vectors. So for vector A, that's about 0.59. This is not in degrees, by the way, this is like in radians. And for A, that would be 0.92. So I know that this whole area is pi radians, and I can find the angle in between. And when I put that angle to the sine, I can find the whole value.